If we're given a function representing distance, can we find speed? How fast are you going? On the other hand, if you're given a function that represents position, which is not the same as distance, can you find the velocity, which is not the same as speed? They're related concepts, but they are different. Let's think about the main kind of example you're going to encounter in many homework problems over this semester. Free fall, where you got a ball falling under the influence of gravity. There's a force of gravity. It's negative mg, where g is the acceleration due to gravity in standard units. G is about 9.8 meters per second, written as 9.8 meters per second squared. That's the acceleration due to gravity. Multiply it by the mass, you get the force due to gravity, or its magnitude without the minus sign. The minus sign keeps track of the fact that the force is downward. If we have an axis pointing upward, say a positive y-axis, then the force points in the negative direction. That's why we have a negative sign right there. All this ends up implying, well, that your acceleration is in fact negative g, is negative 9.8 meters per second squared. And your velocity turns out to equal negative g times t plus your initial velocity. Where did I get that equation? Well, basically from memory. Do you need to remember that equation? I think it would be good to try to. I actually could think of it in terms of calculus. The derivative of the velocity is the acceleration. Let me call the velocity v for short. And, well, okay. Let me give this function a name. What should I call it? I'm going to call it, okay, just f of t here. Just, we're so, uncreative with the function names here. What's the derivative of this function? Same limit. Limit as h goes to 0 of a difference quotient. Now t is the variable because t represents time. T plus h minus f of t, all divided by h. Let me confirm that the derivative of this is this. I claim that's f prime of t, the constant acceleration. The derivative of the velocity is the acceleration. Oh boy, so many letters. Here's my function. G and v sub 0 are constants. V sub 0, or v naught for short, represents your initial velocity. I'm plugging in t plus h into there for t. So many letters, so few numbers. Well, all the letters represent numbers, so it really is a bunch of numbers. There's f of t plus h. What's f of t? Careful about parentheses. It's that. Divide by h. Simplify. Expand this with the distributive property. Negative gt minus gh plus v sub 0. Distribute the minus sign through here. I get a plus gt minus v sub 0, all divided by h. I get some cancellation. The v0s cancel and the gt's cancel. How about that? And I get a very simple limit now, looking limit. Limit as h goes to 0 of negative gh over h. Divide out the h's. This is the limit as h goes to 0 of negative g. That doesn't involve an h. It's negative g. Done. If f of t is your velocity here, then its derivative is this constant, negative g. It is the acceleration. The derivative of velocity is acceleration. Graphically, what's going on here? Say you take the ball and you throw it upwards to begin with. So that v sub 0 is positive. If you throw it downwards, then v sub 0 is negative. Throw it upwards. F of t is going to look like this. It's going to be a straight line with vertical intercept at v sub 0. This is a v-axis and a t-axis. This is f of t. Its derivative is this constant. The slope of the tangent line is constant. That's because it's a line. F prime of t, the graph of the acceleration, is a constant, negative g. That's an a, that's a g. Acceleration is a function of time. The t-axis here is a negative constant, negative g, about negative 9.8 meters per second squared. And that is the derivative of the velocity. It's telling you the slope of the velocity at every moment in time. Constant, negative 9.8, because it's straight. What's your height as a function of time? I need to find a function whose derivative is the velocity. By the way, height is a position, not a distance. It's a position above ground. You could dig a hole in the ground and the height could be negative. If the ground level is height 0 and you're underground, then your height is negative. When you're above ground, your height is positive. It's a position, not a distance traveled. Distance traveled is how far does the ball go as it both goes up and down. Not taking direction really into account if you were to graph distance traveled in that case. I need to find a function whose derivative is the velocity. The height, h, height, is some other function, call it g, I better not use the letter g, h of t. Okay, but that's kind of abusing notation. Though I'm going to go ahead and do it anyway, because scientists and engineers do it. Using the same letter h in both, okay, Harold, let's change it to a y. If I used an h, then I'd be abusing notation. I'd be using the same letter to represent both a variable and a function name. Happens all the time in science classes. Is it a good idea? Well, technically not, but we live with it. H equals h of t. Okay, I called the height y before, so I can get away with calling this y. Y equals h of t. What is the formula for the height as a function of t? It turns out to equal negative g over 2 t squared plus, that's a negative g over 2 there, plus v sub 0 times t plus the initial height, y sub 0. It's a quadratic. And if you graph this quadratic, y is a function of t here, it'll be upside down parabola because the coefficient of t squared is negative. The y-intercept will be y sub 0. It'll look about like this. It turns out that the v sub 0, the initial velocity, is the slope of the tangent line at t equals 0. The slope of that equals v sub 0. More generally, it turns out that the derivative of y with respect to t, h prime of t, is the velocity, f of t. Negative gt plus v sub 0. And you can see if you plug in t equals 0 there, you get v sub 0. You get the slope of that tangent line. In our last 10 minutes, let's continue thinking about this example, but let's plug some numbers in. Okay? To make it easier to think about. But everything I've said here in this general setting is something you should work at understanding. It's not the last time I'll talk about it. So let's use some numbers now. Let's use g equals 9.8. We'll use standard units. Let's take the initial velocity to be, oh, I don't know, how fast can I throw it? Upwards, probably not as fast as sideways. I don't know, 20 meters per second. And if I'm standing and throw it upwards, I'm letting it go at a height of around 2 meters. I might, based on these numbers, want to figure out various things. Like I might want to figure out when's the ball going to hit the ground? When is it going to reach its maximum height? How high does it go? Those are common kinds of things to try to find in physics. We'll save finding those things maybe for Friday. For the moment, let's just write down what the height function is. Based on what I wrote down on the previous piece of paper, it would be this, which will simplify to this. Notice I'm making my T's with little curly cues at the bottom because otherwise they can look like plus signs. This is h of t. I might want to figure out an average velocity. How do you figure out an average velocity? Average velocity, say from time 0 to time 1. From t equals 0 to t equals 1. Average velocity is always displacement over time elapsed. Displacement is another word for change in position, or in this case, change in height. Change in position, in our case, that's a change in height. If it's left-right motion, it's not a change in height. Up-down motion, it is a change in height. Average speed would be distance traveled divided by time elapsed. This height function is a position. Changes in its value do represent a displacement. If it's from t equals 0 to t equals 1, the change in position is h of 1 minus h of 0. And the time elapsed is 1 minus 0. Use this formula, plug in those numbers. I'll be able to do it in my head here. 1 squared is 1 times negative 4.9 is negative 4.9. Plugging in 1 for t. Plus 20 is up to what? 15.1. Plus 2 is up to 17.1. H of 0, plug in t equals 0, you get 2. 1 minus 0 is 1. The final answer is 15.1. Make sure you get the right units. This would be meters per second because it's a velocity. If I throw the ball up with an initial upward velocity of 20 meters per second at time 0, over the first second, the average velocity is going to be 15.1 meters per second. It's going to be 20 meters per second at time 0. It's going to be somewhere close to 10 at time 1 for the velocity, not the height. Average of 10 and 20 is 15, so close to 15.1. And the velocity is a linear function, so averaging those numbers really would be another way to do this. But I want you to be able to do it with this. This is really a difference quotient. And graphically speaking, what we're doing is finding the slope of a secant line. There's t equals 1. The height at time 0 was 2. The height at time 1 was the 17.1. This is not to scale. We're after, in finding this average velocity, the slope of the secant line here. Rise over run. The run is 1. The rise is 15.1. 17.1 minus 2. How about another average velocity? How about the average velocity from, how about t equals 0.5 to t equals 1.5? Let's make it a 2. It's still changed in position, displacement over time elapsed. In this case, it would be h of 2 minus h of 0.5. That is the displacement. Time elapsed is 2 minus 0.5. I'm still using this formula up here. If I plug in 2 into that to find h of 2, negative 4.9 times 2 squared is 4, plus 20 times 2, plus 2. Plugging in t equals 2. 22.4 is the height at time 2. What's the height at time 0.5? Plug in 0.5. Negative 4.9 times 0.5 squared is 0.25. Plus 20 times 0.5 is 10. Plus 2, 10.775. Time elapsed is 1.5. The displacement is 11.625. The time elapsed is 1.5. So your average velocity is 7.75 meters per second over that time interval. Can the average velocity ever be negative? Yes, it can be. This graph's eventually going to come back down. If I pick large enough values of t, my secant lines will have negative slope, meaning my average velocity is going to be negative. Let's graph the function to see where the t-intercept is. Okay, again, we're graphing the original function here. Right there, negative 4.9. Got to use an x in the calculator. X squared plus 20x plus 2. Use a negative sign, right? Yep, okay. Window 0 to, I don't know, 5. Y direction, say 0 to, I don't know, 30, maybe. Maybe. Graph it. Looks pretty good. Looks like it's going to come back down and hit the axis when t is a bit bigger than 4. And it looks like, for example, if I find the average velocity from time 2 to time 4, it should be negative. Let's do that. That'll be the final thing we do today. Average velocity from t equals 2 to t equals 4. H of 4 minus h of 2 divided by 4 minus 2. H of 4 is negative 4.9 times 4 squared plus 20 times 4 plus 2. 3.6. It's smaller. It's close to hitting the ground. H of 2 we've already found to be 22.4. This is going to be a negative number. 3.6 minus 22.4 divided by 2, negative 9.4 meters per second. The speed is the absolute value of that, positive 9.4 meters per second. That's how fast you're going, but the velocity is negative because you're going downward. In section 2.1, these kinds of problems occur, as well as limits of them to get like instantaneous velocity instead of average velocity. Velocity at a moment in time. It's a derivative, really. And they're interpreted graphically in terms of slopes. Okay? Have a good day.